Hello everyone, hope you're having a fantastic day. Today we are going to be working through a slightly more involved example of taking the derivative of an equation using the chain rule. So I have an equation here, y is equal to e to the power of sine of 5e to the x squared. And we're going to find this derivative using chain rule multiple times. So whenever you're using chain rule, you need to identify an inner and outer function. Here you notice that if you kind of look back, kind of see the forest for the trees kind of situation, you notice that y is equal to e raised to the power of a blank. Now that blank is a complex statement, but it's still e raised to something. So that something is what you can attempt to make your u substitution. So out on the side, make a note, let u equals sine of 5e to the x squared. And once you do this, always rewrite the equation in terms of u to make sure you get rid of all the x variable. And indeed, in this case, we do. So long as whatever you choose for u, when you rewrite the equation y, so long as you get rid of the variable x, you can use the chain rule using that u substitution. It is possible to choose too much of a statement for u. So for example, we could have chosen u to be the full equation, e to the power of sine of 5e x squared. And while technically that would work, it wouldn't get you anywhere. You would end up taking the derivative of y equals u, which is 1, and then multiplying it by the derivative of u, which is the derivative of what the original equation was, so you just wasted time. You didn't actually do anything. So always make sure you get rid of your original variable when you do your substitution, but also don't choose the entire equation. Continuing, we need the derivative of y with respect to u according to the chain rule. That's the derivative of e to the u with respect to u, which is just e to the u. But then we also need derivative of u with respect to x, which is this substitution expression we chose, sine of 5e to the x squared. We need the derivative of that. For that, you will actually need to use the chain rule again. So in this case, you need to again choose an inner expression of the function to make your u substitution. In this case, you can note that we're taking the sine of an expression involving x. So we can view sine as our outer function and 5e x squared as our inner function. So we will say let u, and I'm going to mark it u1 so that we don't get mixed up with which u is which. Let u1 equal 5e to the x squared. And always remember, once you choose a u, always rewrite your expression in terms of that variable. So this becomes u equals sine of u1. So we got rid of all our x's, so that means we can use chain rule using this u1 substitution. So again, incorporating chain rule, we need the derivative of u with respect to u1, which would be the derivative of sine of u1, which as we know is cosine of u1. Then we need derivative of u1 with respect to x. That, of course, is the expression 5e to the x squared derivative, or the derivative of 5e to the x squared. And to solve this, we actually need to use the chain rule again. So again, we need to choose an inner function such that when we use that substitution, we get rid of our x variable. There's a couple different things that may pop out to you to try for this one. You could try, for example, to let u2 equal e to the x squared. And that will get rid of your x variable. And then u1 just becomes 5 u2. You can use this and technically use the chain rule on it. Problem is you're going to, again, end up right back where you started. Here's the reason why. If you take the derivative of u1 in this case with respect to u2, you just get 5. But then you have to take the derivative of u2 with respect to x. That's the derivative of e to the x squared. So the complex part of taking the derivative still needs to be done. Rather than making my u2 a full e to the x squared, I'm going to try and see if I can get away with making it less than that. Let's try instead to make u2 just equal to x squared. And if I check myself, that makes u1 equal to 5 e to the power of u2. So I got rid of my x variable, so I can use this u substitution. So when I take the derivative of u1 with respect to u2 now, I get 5 e to the u2. And then I take the derivative of u2 with respect to x. That's the derivative of x squared with respect to x, which is just 2x. So now I finally completed the chain rule. I have the derivative of u2 with respect to x. I have the derivative of u1 with respect to u2. I have the derivative of u with respect to u1. And I have the derivative of y with respect to u. So putting these all together, applying the chain rule, we can make the statement that the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to u1 times the derivative of u1 with respect to u2 times the derivative of u2 with respect to x. And so, now that we know those four components, it's just a matter of putting them together and multiplying. So putting in what we've calculated each of these derivatives to be, we end up with e to the u times cosine of u1 times 5 to the power of u2 times 2x. And of course, your last step is going to be to look back at your work and what you wrote as each u to be, and then unsubstitute the u's so that you end up with an expression only involving one variable, that being x. So the derivative of y with respect to x is e to the power of sine of 5 e to the x squared, because that's what we chose u to be, times cosine of 5 e to the x squared, because that was du with respect to d1, but with unsubstituted u1, times 5e to the x squared times 2x. Last step of any math problem is always to simplify any that you can. So I'll make that a 10, and I'm also going to multiply the e to the sine of 5e to the x squared times the e to the x squared. So the derivative of y with respect to x becomes 10 e to the power of sine of 5e to the x squared plus x squared times cosine of 5e to the x squared times x. And that is the derivative of y.